The one on the left is not one of mine, but these are the ones on the right. And what you see on the right is convection. These are temperature contours. And what is happening, this is a cylinder here, and it's heated from below and cooled from above. So a cylinder, you know, like a can of beans, right? And it's heated from below and cooled from above. You might think that I was rotating it, right? But I'm not. This is a cylinder that's being kept stationary. I mean, it's just sitting there, and it's hot here and cold here. When is there spontaneous appearance of motion? I don't just mean fluid motion, because fluid motion, if we just have a roll that's described like this, that's a stationary state. The velocity at any point is non-zero, but it's the same at any time. Whereas you can see here that the flow, that at different times you have different states. This red patch of temperature has moved, right? You have, yeah. Everybody understand what I'm saying? If we describe, if we have a velocity field, the particle that's non-zero, the particles are moving, yes. But if we were to draw, to snap a picture of it, its temperature or its PIV or something, those arrows would stay where they are. And the hot patches and cold patches, whatever, would stay where they are. That's what a stationary state is. So even though there's velocity, the u of x, y is non-zero, but it is not changing in time. These are obviously fields that are changing in time. You're hot here. If I stand here, I'm not so hot. Now I'm hot. Now I'm not so hot. Now I'm hot. Now I'm not so hot. Now I'm hot. So too, if I'm here, hot, not so hot. Hot, not so hot. These are the same fields as this, but viewed in the middle. This is a slice through the middle. You see here the same rotation that you see here, but here you see it in a plane like this. And here you see it from the side. Okay? And what would you call these two things? Let's call them both waves, and then let's put an adjective in front of that. What would you call these? What kind of waves? These are traveling waves, just so. Rotating or traveling or translating waves, yes. And what would you call these? Stationary waves, exactly. These have nodes. I can have a line here, and it's going to oscillate about this line. This is standing wave, and this is rotating wave. Right? And these are situations that arose merely from heating from below, without doing anything that's time dependent. I'm not rotating it. I'm not changing the temperature in time. This just happened spontaneously. That's one of the many nice things about multiple solutions and fluids and bifurcations and so on. In contrast, let me show you this. This is also a time-dependent flow like this, but you don't. It has kind of the properties of traveling wave, but not really, because it's not exactly the same here as it is there. Whereas this one really is exactly the same. Moving in space and moving in time are equivalent. And that's not so here. This little structure is changing as it gets big, but it's like a traveling wave. Okay, so we're going to talk about the understanding of these things. View, full screen mode. There. Okay. So, that's all it needs to be. So we're going to talk about a new situation. Again, we're going to talk about O2 symmetry. The same thing we've been talking about, whether we have that operator S theta and the operator kappa. And we're going to talk about what happens when you have a Hopf bifurcation. Before it was a steady state bifurcation. What leads to this is this circle pitchfork is to a steady state, one of many steady states, a whole circle's worth of them, but steady. Whereas here we're talking about a Hopf bifurcation. Hopf bifurcation leads to time-dependent behavior. Okay. And now we're going to do the analysis. And that is what you were seeing before. Here, these pictures here. These pictures here are the result of a Hopf bifurcation with O2 symmetry. And so these words, all this mathematics, all these symbols, here you have a picture of what's happening. Let me ask you a couple of questions. O2 symmetry, that refers to rotation and reflection. What kind of rotation and reflection do you think we're talking about when we have this can and we have heated it from below? Rotation and reflection in which variable? In theta, just so, that's right, here. So we have rotation, reflection, symmetry in this direction here. And the rotation you can sort of understand, that is to say, all the angles seem the same. But what about reflection? Remember we talked about the difference between O2 and SO2. This thing is moving around in this counterclockwise direction. How do you explain that? Why is it moving around? How is it moving? How can it move around when you had this reflection symmetry in theta? You know the answer to this. Why is it it's rotating in this counterclockwise direction, and yet there's symmetry in reflection in theta. Does there seem something wrong with that? Is there something wrong with that? Well, first of all, I'll tell you, no, there isn't something wrong with that. This is my work. Of course, there's nothing wrong with my work. But how do you explain that? Why is it going around the counterclockwise direction when it has a symmetry in reflection symmetry in theta? How does it know to go counterclockwise?
It doesn't. You could have gone clockwise, but it just happened.
Just so. Exactly. This is someone who has understood the principles of the class. There is a solution like this. There exists another solution in which it goes in the other direction. Necessarily. You know this without even running the simulation. Otherwise, yeah, you favored counterclockwise if it comes out counterclockwise. There is another solution where it goes clockwise. This is random. It's not exactly random because, say, my loops, in Fortran went from 0 to 2 pi and not from 2 pi to 0 or something, some trivial thing like that. But all I need to do is change some very trivial thing and it will go in the other direction. It won't be random in a calculation because when you run a calculation, you will always get the same thing, right? So I will always get it going that way because if you run a calculation, but in an experiment, it'll go the other way. Possibly that's even true in an experiment. Your experiment is never exactly symmetric either, and perhaps it will always go in that direction. But still, to very, very close approximation, you could make it go in the other way, and that's equivalent. Okay. Now, what about this cylinder wake here? It's going in this direction. It's not. What can you say about it? Just so. This one here is not there is no symmetry left-right. This is the classic cylinder wake. You have this cylinder that comes out here, and you have imposed a flow like this. You're blowing at it. I can't. So Navier-Stokes is, of course, reflection symmetric, but your boundary conditions are not. Your boundary conditions are that there is far-field flow this way. You're telling it to go this way. There is no corresponding solution that goes that way because going this way and going that way are different in that situation. You've done that as an experimentalist or computationalist. You have put in a velocity that goes to the right, but not in those situations. These situations have O2 symmetry. All the thetas are the same, and clockwise and counterclockwise is the same. And therefore, if you have a rotating wave, you necessarily have one in the other direction. This one does not have that symmetry. The only symmetry that this one has is a reflection symmetry about this, about that axis. Okay, so now let's go back to some equations and let's see this happen. Because notice, okay, we talked about how there's rotating in the counterclockwise and the clockwise direction, but what about this other thing? What about these other waves? Here, we have standing waves as well, right? Why is that? What's going on? Okay. So that's what the rest of the class is about. It's about just that situation. So supposing you have a Hopf bifurcation in a situation where you have O2 symmetry, That, yes. Okay, again, I'm just going to tell you this. I'm not going to derive it. I'm going to tell you that we describe this with two complex modes, which we'll call Z plus and Z minus. So we have four scalars altogether because Z contains an X and a Y. And so we have an X plus, an X minus, a Y plus, and a Y minus. And the plus, of course, refers to things that go to the right, and the minus refers to things that go to the left, of course. And, okay, so a lot of these things I'm just going to declare, and you just take my word for it. And there are books in which it's derived properly. I'm not sure I ever got through it. But we write our functions like this, and you can see that this could be temperature or anything you want. A real variable, you can see it's real, it's something plus its complex conjugate. Okay, so this is an okay velocity field described by these two complex amplitudes, Z plus and Z minus. How does this evolve? Remember, this is going to evolve in time by evolving these amplitudes, Z plus and Z minus, and at linear order, we have evolution like this. Z plus goes like e to the I omega, e to the I omega, and Z minus goes like e to the minus I omega. You can see how this wave is except the other way around. This one goes in the, I always get mixed up, positive, negative direction. Anyway, this one and this one go in opposite directions. One of them is left going, one of them is right going. One of them is clockwise, the other one's counterclockwise. Right? You see that here. Okay, now we do the same kind of exercise as before. We have the, we're going to act with the rotation operator on this, now not on just a Z, but two Z's, Z plus and Z minus. And when we act with S theta naught, we multiply with, a rotation by by theta naught, that's like multiplying it by e to the I theta naught. So again, just accept this. This is just declaration. I'm not deriving it. I'm only telling you. Kappa says to complex conjugate, so we complex conjugate. If we were to do all that kind of thing that we did before, like when we did it here, right, we got the G had to be odd and even, and then when we did it, when we did this here, and we learned that you had to have only these terms, you turn the crank. But let's not do that. We don't have time. We don't want to do more turning the crank. I will just tell you the answer is that in order to have commutation of your right-hand side, which gives you the evolution of Z plus and Z minus in time that commutes with S theta naught and kappa, in other words, that respects the O2 symmetry, that does not favor clockwise or counterclockwise, and does not favor any particular angle. All the angles are the same to it, and going clockwise and counterclockwise are the same to it. That tells you that the operator here has to commute with these. And the simplest thing that does commute, truncated to cubic order as usual, where the first nonlinear order where you have any non-trivial behavior is this. We do not have all the possible monomials. We've cut them down we've eliminated them by making them commute with these. I'm just telling you saw that exercise a couple times, and that's enough. Okay, so this is the evolution equation for Z plus and Z minus. Okay, and I remind you, what is Z plus and Z minus? We're writing our functions of theta and time as a product of a periodic spatial function times an amplitude that varies in time. And again, as I say, I like to go from the ground up, really, really understand. And I'm not, but this is not really giving you that. This is just telling you that. Just accept it. I'm not pretending I've done anything more rigorous than that. I'm just telling you, it's just accept it, and just accept this thing here. Okay, now let us do our usual thing where we put in for Z a polar representation because it's going to give us more insight. So when we do that, when we put Z equals RE to the I phi, and we substitute in and we do our R dot and our theta dot, and then we separate our equations, this is what we get. And we're starting to get used to this. We have a term that is linear in R plus, that mu R plus or minus, and we have cubic terms with 3 powers of R. We're used to that. We've seen that now many times. And for the phi dot, again, we're starting to see things like this before. We have a constant term and an omega, that's like an angular velocity, right? We see a plus or minus, which is again telling us, counterclockwise or clockwise, and that depends on whether you're z plus or z minus. And then we have other terms here, and that's similar to what we saw before. Now I told you that in order to commute, you had to be in this form, and then I told you that the polar representation of this was this. Now, let's just take this as a given, and let us now reason from that. We see that these equations do not depend on phi, and that is as it should be. If there were phi's in here, that would be telling you that there were special values of the angle. The fact that there's no phi tells you that all the phi's are the same. If you had a phi occurring here, a cosine phi, a phi squared, anything, it would be distinguishing different values of phi. Okay, so this tells you something physical, something phenomenological, something brings you knowledge. There is no phi here, all angles are the same. Okay, well, we expect that, but you can check and make sure that you've done things right, and you see that there's no phi. Let us look at these R equations here, and let us look for, okay, we're never going to find fixed points. It's a Hopf bifurcation. It's not fixed points we're looking for. We're looking for rotating wave, something time dependent. Okay? But we might find something that's rotating, say, so phi dot is not 0, but maybe R dot is 0, maybe. So let us look for solutions to this cubic equation, cubic in two variables. Okay? And we see there's several. We can see this right away. We can have a fixed point for the R equation that has R equals 0. We can have R plus be 0 and R minus be 0. And what's that? That's the origin where there's nothing happening. That's my conductive state, and here's my can, and it's just sitting there, and it's not doing anything. There's no motion. The solution is U equals 0. Temperature is the linear profile. It just sits there. That's R plus equals R minus equals 0. Okay? So that's our first solution here. We can also have, we can have other solutions. We can say, let's make R minus equal to 0, but R plus not equal to 0. And if we carry out that calculation, we find that that is a possibility. We can have one of them being 0 and not the other. And notice that the coefficients are such that whatever happens with the R plus also happens with the R minus, just the same. It has to be, because that has to do with the right going versus left going. So we see that. If we look for just things that have R plus and no R minus, this is the value of R plus here. If we look for ones that have just R minus and no R plus, we have just the same value here. And we put in these values, the R plus and the R minus values, and these are going to give us these speeds, these phi dots. Okay, we're going to put in the values of the R plus and R minus, and we'll get something that's like omega, it's like plus or minus omega, with other stuff. Okay, and that's what we see. This is going around at some speed, and this is going around at minus that speed. So these are the left going ways and the right going ways. We can also now look for solutions where neither is 0. And, again, you just have to plug in this little cubic equation, and you can find that there are solutions where neither is 0. That is to say, where this term is not 0, and you're satisfying this equals 0 for the plus equation, and this equals 0 for the minus equation. Okay, and then you get that R plus and R minus are this value, and phi dot has this value. I mean, there are two different phis. One goes plus and minus. And so these are indeed the left waves and the right waves and the standing waves. Okay, so we've done some math and some calculation, so on. But there's more to, okay, these are just pictures for if I don't have a film, but you saw the film, so you've seen these things moving around. Okay, yeah, you've seen, this is obviously a traveling wave, it moves in one direction, and this one here is obviously a standing wave, it has some fixed nodes. Okay, now we can do some more calculation. We can do Jacobians. Okay, so we go back here and we look at these things here, and we take the derivative of this top equation with respect to R plus. We take the derivative of this equation with respect to R minus. We do the same thing for the minus equation. We take the derivative of this thing with respect to R plus or R minus. Of course, if we take the derivative with respect to any of the phis, we have 0 because there is no phi over here, and that is reflected in the Jacobian over here, you see, those are the derivatives with respect to the fees, and there is no derivative at zero. There's no dependence on the fee. That's what these two columns are telling you. These are the partial derivatives with respect to fee plus, the partial derivative with respect to fee minus. These are the partial derivatives with respect to R plus. This is the partial with respect to R minus. Okay, and now this tells us we can simplify our search for these eigenvalues. It's not, okay, we've said several things about matrices. We've said that matrices that are block diagonal have as their eigenvalues the eigenvalues of the blocks. We've said that matrices that are upper or lower triangular have their matrices along the diagonal. But we can say more than, we can put those two statements together. We can't always do that, but in fact, I'm telling you, you can. If you have a matrix which is block triangular, as is the case here, block lower triangular, then again, the eigenvalues are the eigenvalues of the blocks. So that tells us that we only need to look for these, the eigenvalues of this and the eigenvalues of this. The eigenvalues of this are 0. So we only, it turns out, then we can, okay. Again, what does it mean for eigenvalues to be 0? It means I don't care. And what is that telling you in these terms? In these terms, it tells you, imagine if I were to do, imagine if I were to take this field here at a certain time, and I stop it, and then I move everything over, and I start it rotating. Is it going to be upset? No, it doesn't care that you have moved it by some angle. It will just start moving from wherever it is. It has no particular love for any phi. And this one too, supposing this one, you can see it has an axis here, and it stays at that axis. Supposing I were to take this and I would give it instead this axis here, and it's going to, you can imagine it's not going to go back, ooh, wrong axis. It's going to keep doing its thing around the new axis. That's what it means to have rotation symmetry. It doesn't care. And that's what those phis, that's what these two eigenvalues tell you here, the fact that they're 0. Then there are two more eigenvalues in the R plus and minus directions. And for here we use my favorite formula. This is a formula you do not learn, I believe, at least I never did, the eigenvalues, the formula for the eigenvalues of a 2x2 matrix. Am I right? Nobody, it's not like the quadratic formula. But ever since I learned it, which was fairly late, I use it all the time. And I don't know how people get along without it. I will tell it to you, and I think you will find too that it is worthwhile to memorize it. The eigenvalue of this 2x2 matrix are the average of the diagonal terms, meaning the trace over 2, if you like, but I prefer to think of it as the average of the diagonal terms, plus or minus square root of the difference between those diagonal terms over 2 squared plus the product of the off-diagonal terms. I can't guarantee, I don't know quite what you study, what your problems are, but I find this formula incredibly useful. I use it at least once a month. So there, I tell you, and if you keep those words in mind, the average of the diagonal elements plus or minus the square root of the difference over 2 squared plus the product of the off-diagonal. Okay. This is going to tell you, in fact, something right away that has nothing to do with what I'm going to say later. But notice you can only get complex eigenvalues if B and C are of opposite signs, because you need to have a square root of a negative number, and this part is always positive. Right? So that tells you something right away. Okay, so let's look at this picture. What is this picture? This axis here, okay, this is like when we did the unfolding of the pitchfork. We have a set of parameters, AR and BR. What are these AR and BR? You recall over here we had A and B, and we have the A and B are complex here. Here they are, but they're only in the phi equation. The R equation is the only one we're looking at now, and that concerns AR and BR. And those are the two parameters here, multiplying the cubic terms. And the situation that we get depends on those values of AR and BR. So we've now drawn the AR-BR plane, AR-BR, and we've drawn a bifurcation diagram at each point in the AR-BR plane. Oh, I've just noticed it's kind of the opposite of what you think. A is the vertical axis, B is the horizontal axis. So these pictures are R, both R plus and R minus, say, as a function of mu at every point for all these different values of AR and BR. And you can see there are here 6 different cases. So what are these things? You know what they are, we've already seen them. The traveling wave solutions look like this, and you see that they, let's take BR negative. They only appear for mu positive here, if BR is negative here. The traveling wave solution, and the other one has just exactly the same properties, and the standing wave solutions are like this. Okay? So depending on the different signs and the relationship between AR and BR, you either have both the standing waves and the traveling waves appearing for mu positive, or you see that it depends, I mean, that's easy to say mu positive for this and this. That's if BR is negative. Here, what you're going to depend on is the quantity AR plus 2BR. Is it positive or negative? So this, according to AR plus 2BR, it's going to branch to the right or to the left, depending on on the sign of AR plus 2BR, and that tells you whether you are to the right or the left of this diagonal line. This is AR plus 2BR, is positive over here and negative over here. Okay? So those are the 2 things you're looking for, is the sign of BR and the sign of AR plus 2BR. So according to those signs, you either have the standing waves and traveling waves branching to the right or to the left, and they might branch in the same direction or the opposite direction, depending on whether BR or an AR plus 2BR have the same sign or the opposite signs. So those are all the different cases, and the stability is drawn also. In this case, we see that the standing waves are stable and the traveling waves are not. And in this case here, where AR is is negative, we see that the traveling waves are stable and the standing waves are not. Over here, we have the standing waves and the traveling going to the left, and they are both unstable. And when they branch on either side, on opposite sides, they are always unstable. And all this you can get by looking at the eigenvalues of this little 2x2 block. This makes a 2x2 block. You calculate those eigenvalues with this formula, and you will find that. The eigenvalues, in fact, they are here when you calculate them. But okay, they look very complicated here, right? They look complicated, but in fact, when you substitute the values of R plus and R minus, a lot of that complication goes away. Here you have R plus squared equals minus mu over BR, and you can see that if you do that, you have minus mu over BR. That BR goes away, for example. If you plug that into this, you'll find that it's simple, and in fact, how simple is it? It's this simple. These are what the eigenvalues are for the 4 different fixed points that we found for the R equations. The first one we found was the origin, where the fluid wasn't doing anything. And there you find that the eigenvalue is mu in the R plus direction and mu in the R minus direction. So that looks a lot like these things that we're seeing. That is to say, the same eigenvalue in the 2 directions. If this is the R plus direction and this is the R minus direction, either we have the eigenvalue negative or positive. It's the same in both directions.